Okay, before we get started on these guys, just a couple of reminders. Okay, your lab report for the Properties of Compounds lab is due February 13th. Okay, so day after tomorrow. Make sure you've got that done for 8:30 a.m. Submitted through Google Classroom. I have had a couple of people come in to have theirs looked over. Okay, but it's still a good idea for you to do that. I'm available today at lunch and scheduled help if you want to pop in. It only takes a couple of minutes for me to read it over, okay, but it's time well spent. Also, reminder that this week's quiz will be on properties of compounds, naming, and solubility. Okay, the reaction stuff that we go over today will not be on this week's test, but it will be on the week after the break. Right, so it's going to be something we're going to be spending a lot of time on over the next while. Okay, number 5, ionic or molecular? Okay, is it 2 nonmetals? Yeah, phosphorus, okay. Plus, we also see a prefix. If it's got a prefix in it, it's a dead giveaway that it's molecular. All right, how many phosphorus are there according to that formula? Just 1, right? There's no prefix on it, so it means 1. Okay, and trichloride means how many chlorines? 3. PCl3 for that one. For number 8, is that ionic or molecular? Molecular. Oh, sorry, no, number 8. Sorry, ionic. It's got a metal, right? Cobalt is a metal. If we see a Roman numeral, it's always ionic. Okay, Roman numerals are only ever going to be present in an ionic compound, okay, because they're only ever present on metals. So, cobalt. If it's ionic, I write the symbol for the metal and its charge. Cobalt has more than 1 charge. Does the Roman numeral help me with that? Yeah, it tells me what charge to use. This is the cobalt that is 2+. And it is with nitrogen, which is a -3. All right, so that's the first step of doing the formula for an ionic compound. Write the symbols of the elements and their charge, and then drop and swap. CO3, N2. Okay, and we're done. All right, number 10, ionic or molecular? Ionic, okay, it's got a Roman numeral, nickel's a metal. Okay, so nickel, this is the nickel with the 2+ charge according to the Roman numeral. It is with fluorine. Fluorine is in group 17, where everything has a -1 charge, and I drop and swap. Okay, we don't write 1s, so I don't need to put a 1 beside the nickel. Okay, if you got questions on these guys, you get any of them wrong, okay, don't be afraid to ask. Okay, you're probably not alone. All right, number 11, another one with the Roman numeral in it, so another ionic compound. Something I see happen a lot, I know it happened earlier because a few people had mentioned it, manganese and magnesium, they're easy to get mixed up because they sound a lot alike when you say them, okay? Just make sure manganese is always going to have a Roman numeral because it's got more than 1 charge where magnesium doesn't. Okay? So manganese is Mn, and this is the manganese with the +4 charge, and it is with selenamide. Okay, selenamide is in group 16, so it's a -2, right? Okay, so when we drop and swap, there's a trick with this one. I get a 2 here and a 4 here. Am I finished? No, what do I need to do? I need to simplify. Do I only do that with ionic compounds? Yes. Okay, so we got MnSe2 for that. All right, now guys, that is one I would totally make a multiple choice question. All right, would I make Mn2SE4 one of the options in the multiple choice? Yes. Absolutely. Okay, and it'll catch people. All right, just, you get anxious on a test, you're not thinking, you do the drop and swap and you think you're done. Okay, that's where really having a lot of practice under your belt for things like that is important. Okay. All right, number 13, ionic or molecular? That one's molecular. We got prefixes, they're both nonmetals. All right, how many oxygens according to that name? Just 1, there's no prefix in front of it. And how many fluorines? 2, OF2. All right, and number 16, ionic or molecular? Molecular's got prefixes, they're both nonmetals. How many silicon? 2. How many chlorines? Okay, now, why did I put this one on here? Because it's what? Was it on our quiz? Oh. Okay, sorry, yeah, you're right. That is a valid answer. Could you have one like this on the quiz? Yes, you could. Do I reduce this one?
No.
That's why I put it on here, okay? Just to remember those rules, okay? We want to practice as many of these as we can that have those special little rules, okay? This one, lots of people would reduce it, okay? They would over-apply that rule that only applies to ionic compounds because they see this could go lower. All right, everybody with me there? All right, just little things like that that we want to keep in mind. All right. Now, I've got some review questions on here that I want you guys to write down and try, and then we're going to go through them together. Okay, this is basically all the stuff from lesson 4 to where we are now. Okay, just to practice a little bit and review what we've been doing. All right, so a couple of just fill in the blank here. Okay, it's not a quiz, not coming in from us, it's just for review. Okay, and then for these ones here, okay, I want you to name them, and I also want you to tell me whether or not they are soluble, except for this one and that one. Okay, those ones you can name, but they're not going to be on your solubility chart because they're just not. Oh, sorry, never mind. These are the ones I want you to do the soluble for, just these ones here. Okay, so it's actually columns like this. I forgot how I set this up. So name these compounds, write the formulas for these compounds, tell me whether these are soluble or not. Sorry, I forgot how I set that up. Okay guys, let's go through at least a few of these here. So number 1 relates to the lab that we did. What was the one test in that lab that would unequivocally every time tell you whether the substance was ionic or molecular?
Was it the conductivity?
Right, it was the aqueous conductivity test. When you tested the solution for conductivity. Okay, so definitely, yeah, answer for that one is conductivity. Is that the kind of thing I might ask on a quiz? Absolutely. Okay. A substance that dissolves another substance is a solvent, right? Okay, a mixture with 2 visible parts is a heterogeneous mixture. We could also say mechanical mixture. Okay. So 4, 5, and 6, naming here. So for number 4, okay, is this ionic or molecular? Ionic. Lithium is a metal, right? Okay, do I need prefixes in an ionic one?
No.
No. Okay, so I'm just going to write then the name of the metal and the name of the non-metal, ending in I. Do I need anything else? Does this one need Roman numerals? No. Lithium only has one possible charge. We're done. Lithium nitride is the final answer. Okay, number 5, ionic or molecular? Molecular, they're both non-metals. Okay, what prefix do I need to put in front of sulfur? Okay. Trisulfur. Dinitride. Okay, and then for our last one here, ionic or molecular? It's ionic. Lead's a metal. Nitrate is a polyatomic ion. So I'm going to write the name of the metal, lead. I'm going to write the name of the non-metal. Okay, in this case, it is a polyatomic ion. So I'll just write its name as it appears. Okay, am I missing anything? What do I need here? I need the Roman numeral, yeah. Okay, so what I do is I look at nitrate. Okay, nitrate is a -1, and there are how many? 2 nitrates, so I've got a total of 2 negative charges. So I've got to get 2 positive charges from 1 lead. So this lead has a charge of 2. Lead, Roman numeral 2, nitrate for that. Okay. Questions on those? Okay, how many people are done 7, 8, and 9? Okay. So for writing the formula here, okay, for potassium carbonate, ionic or molecular? Ionic. Potassium is a metal. Okay, so the formula or the symbol for potassium is K. It's a +1. Carbonate is a polyatomic ion, CO3. It has a charge of -2. All right, now what do I do?
You just drop and swap.
Now I drop and swap. Okay, so the 1 drops, it comes over here, we don't write once. Done with that. The 2 drops and comes over here. K2CO3. You could write it like this or like that. Okay, as long as you don't have a number outside of those brackets. Okay. Questions on that one? Number 8, iron 2 phosphide, ionic or molecular? Ionic. Iron is a metal. Okay, so what does the Roman numeral tell me to do with iron? Has a charge of +2. So I put the 2 up there, okay, and it's with phosphorus, which is P, and its charge is -3. Now what do I do? Drop and swap. All right, so the 3 drops and comes over here. The 2 drops comes over here. All right, I can't reduce that any further, so I'll leave it like that. Okay, questions there? All right. Number 9, disulfur trichloride, ionic or molecular? Molecular, full of prefixes. Okay, how many sulfurs do I have?
2.
Okay, how many chlorines?
3.
Okay, we're done. All right, then our solubility charts. We got to figure out whether these are soluble or not. Okay, so sodium sulfate. So I look up sulfate, it's right smack in the middle of my solubility chart. It says it is soluble with most things, which is not helpful, so I have to look down to the row below. Sodium is not in that insoluble row, so this is soluble. All right, silver chloride. So I look up chlorine, it's in the column just to the left of sulfate. Okay, it says it's soluble with most things, but in the row below that represents insoluble, I do see silver there. Okay, so this stuff would be insoluble. All right, and then potassium hydroxide. So OH is the last column on the right, and it says it is soluble with group 1 ions. Is that where potassium is?
Yes.
Yeah, potassium's in group 1, so this is sodium. Okay, guys, that is a taste of what you are going to see on Friday. Okay, your quiz on Friday will contain the same types of questions. Right, there might be some fill in the blank with terminology that wasn't on here from like the solubility stuff, and there'll be a little bit of stuff on the polar nature of water as well. Okay, so know your cohesion, adhesion. Okay, electrons aren't shared equally in a polar molecule, that kind of stuff. Make sure you go over that. Okay, but otherwise, that's the stuff that'll be on there. Those skills will definitely be on Friday's quiz. All right. So today we got to go over writing chemical equations. So what we'll cover today are basically the 5 types of chemical reactions that we will go over. There are more than 5 types, but we're looking at these basic 5 types. Okay, how do I know a reaction has occurred? What are some signs of a chemical reaction? There could be a temperature change. There could be a precipitate form.
Bubbling.
There could be bubbling and fizzing. Bubbling and fizzing means what's being produced? A gas, yeah. Okay? Sometimes you can get a gas produced, but there won't be any bubbling and fizzing. What would be a way to detect it then? Smell. Yeah. Sometimes there's an odor change. Okay? In your reactions lab that you're going to do after the break, okay, there is a reaction. No signs. Like you mix the 2 things together and it doesn't look like anything happens, and then suddenly it's like someone broke one of those smelling salt things right under your nose. Okay? It will literally curl the hairs in your nose. Okay? But there's no other signs that a reaction is occurring except that suddenly there's this very strong odor. All right? What else? Surprise, this is usually the first one.
Color change.
Color change, yeah, color change is going to occur in a lot of reactions as well. All right? So all of these are signs of a chemical reaction. Here's what we have to understand about those signs. They mean that new materials have been made because we're seeing a change in the physical properties between our reactants and our products. Right? Like, for example, one of the reactions that you're going to do in this lab, you're going to mix 2 clear solutions together. Okay? It looks pretty boring to start. And at the end, you're going to have a precipitate. It's going to be brightly colored. Okay, all of those those are both signs of a chemical reaction. Okay, but they're also signs that the stuff you've made in this reaction is chemically different than what you started with. Because what you started with was two things that were soluble in water and were clear. And what you ended with was something that was soluble and something that was insoluble and was brightly colored. Right? So there's signs that in that reaction, you have taken the elements that you started with and you have rearranged them somehow. Okay? Back to Dalton's fourth point of his atomic theory, right? In a chemical reaction, atoms can be separated, they can be joined, or they can be rearranged. The signs of a chemical reaction are why he thought that and why he was right. Okay? In a chemical reaction, we don't change what we have, we just change who it's with. Okay? So, to give you an idea here, a chemical reaction is laid out like this. Okay? We could have, let's say, compound AB plus compound CD, right? And then we'll have an arrow. These are our reactants. Okay? Because they're the things that are going to react with each other. Okay? On the other side, I still have the same things, the same elements, that is. But now, they're with different partners. So this would be one of those rearranging reactions that Dalton described in his atomic theory. Okay? I haven't created any new elements, but I've created new substances by rearranging the elements I started with. Everybody follow me there? Okay? So this side of a chemical reaction is called the products. Because it's what's produced in reactions. Sometimes we try and make things make sense. Right? The reactants are the things that react, the products are the things that are produced. Okay, everybody good with that so far? All right, so we talked about the signs of a chemical change. We're going to go over the types of reactions. Okay, we're going to look at how to identify each reaction type. That is something you'll have to be able to do because eventually we're going to get to the point where I will only give you the reactants and I will ask you to predict the products. Right? To do that, you have to know the 5 types and their patterns. Okay, which is actually a lot easier than it sounds. Okay. All right. So, in a chemical reaction, the final products are chemically different from the starting reactants. They contain the same elements, but they're chemically different. They have somehow been separated, joined, or rearranged. Okay? So, super important to recognize that is always, always true. Okay, questions on that idea? Okay, so yes, they're chemically different. Can you get them back? If I have a chemical reaction, can I get my reactants back after? Okay, is a campfire an example of a chemical reaction? Okay, can you get the wood back? No. Okay, there are some reactions that are reversible. Okay, not all of them, very few of them in fact are reversible, but some are. The chemical reaction that powers your phone is reversible. But what do you have to do to reverse it?
Use it.
You have to what?
Use it.
You have to use it. That's going to drain the battery. How do I charge the battery? I have to put in what? Energy. Yeah, I got to plug it in, right? I got to put energy in to make the reaction go back. Okay? In any type of battery, a chemical reaction is what's producing the electricity. If you want the battery to go back to the original state, you've got to put all that energy back, okay, in order to get it back to that original state. Okay, those are more the exception than they are the rule. Most chemical reactions are one way. Okay, you're gonna have your final product and that's it. All right, first type of chemical reaction that we're gonna talk about is the simplest one, and it's called a synthesis reaction. In a synthesis reaction, okay, two or more elements will react or combine to form a single compound. Okay, so a synthesis reaction has an easily recognizable pattern. In fact, all of the reactions have an easily recognizable pattern. They are all considerably different from each other. Okay? In a synthesis reaction, you will always have two reactants and one product. Okay? You are synthesizing one thing from many in a synthesis reaction. This is the only reaction type where you will have only one product. All right, so we've got an example one here, okay, where I have magnesium reacting with oxygen to form magnesium oxide. Now, just so you know, the little things in brackets here indicate the state of matter. That is not something you have to put in your reactions in Science 10. Okay? It's just telling me that I have solid magnesium, I'm reacting it with oxygen gas, and that produces magnesium oxide, which is a black powdery solid. Okay? So you don't have to worry about putting these in any of your reactions for Science 10. Okay? What are these big numbers? If that was an equation in math and you had a big 2 in front of something else, what would it mean you do with that 2?
Multiply.
You would multiply it. Okay? So what this big 2 means is that there are 2 magnesium atoms. And they're reacting with one molecule of oxygen. How do I know that this means 2 magnesium atoms and this means one molecule of oxygen?
Because of the size of the number.
Right, the size and location of the number. If it's a big number like this, it means multiply everything behind me by 2. Okay, that's what we do. That means 2 separate magnesium atoms. They're not bonded together. But if I have a little subscript number, that does mean these things are bonded together. This is a molecule made up of 2 oxygen atoms. Okay, everyone follow the difference there? Okay, being able to interpret the numbers in a chemical reaction is a very important skill. Okay. On this side, I have 2 molecules of magnesium oxide. Right? How do I know that? Well, the magnesium and oxygen are written beside each other, and the 2 is in front of it. Okay? The 2 means multiply everything behind me by 2. Now, the reason we put those big numbers in is so that the equation is balanced and follows the law of conservation of matter. Okay, or the law of conservation of mass, whichever way your teacher taught it to you before. Matter cannot be created, and it cannot be destroyed. Okay, that means I have to have the same number and type of everything on both sides of the reaction. Otherwise, I'd have created or destroyed atoms, and I can't do that. Right? So on this side, there are 2 atoms of magnesium. Are there 2 atoms of magnesium on this side? Okay. On this side, how many atoms of oxygen are there? Still 2, right? There's 1 oxygen molecule made up of 2 oxygen atoms. On this side, that 2 applies here. There are 2 oxygen atoms on this side as well. Okay? That equation is balanced, and I haven't created or destroyed any matter. Okay? All right, so in a synthesis reaction, it's any two elements combining to form a single compound. So we could have this as well. Okay, in this reaction here, I have two atoms of potassium reacting with one molecule of bromine, made up of two bromine atoms, and then I would get two molecules of potassium bromide on the other side. Okay, do I still have two of everything on the other side? I do. Sometimes it's easier to see it diagrammatically like that. Okay? All right, so the pattern for synthesis is two reactants, one product. Okay? All right, next reaction type is the opposite. Okay, in this one, we're synthesizing. In the next one, we're going to take that single compound and we're going to break it down. Okay. All right, so the next reaction type we call simple decomposition. Sometimes we just call it decomposition. That's fine if you just write decomposition. Okay, in a decomposition reaction, a single reactant decomposes or breaks down into its elements. Right? So it is in every way the exact opposite of the first one. Okay. So the reaction you see there is the one that nearly killed Mark Watney in The Martian. Okay, if you recall, when he nearly blew up the hab and singed off his eyebrows, okay, he was trying to make more oxygen, okay, out of the water that he had. So he was splitting the water into hydrogen and oxygen, and he blew up all the hydrogen by accident. Okay, that's the reaction he was using. Right, so the pattern for a decomposition reaction is a single reactant, two products. Okay, those products are usually elements. Okay, in that reaction, how many hydrogen atoms do I have here? 4. Okay, remember, this big 2 you told me in math, that means multiply the stuff behind me by me. What's 2 times 2? 4. Okay, so on this side, in the reactants side, there are 2 times 2 hydrogen atoms. How many oxygen atoms are there? 2, right? Because there's a 1, an imaginary one, beside that oxygen. 2 times 1 is 2. Okay? Now, on this side, on the product side, are there still 4 hydrogen atoms? Yes. Are there still 2 oxygen atoms? Yeah, but they've been rearranged. They've actually, in this case, been separated. This is the one Dalton was describing when he said atoms could be separated. Joined or rearranged, this is separating. Okay, the first one was joining. Okay, so diagrammatically, you could have a reaction that looks like this. So we would have 2 molecules of nitrogen triiodide, and they would break down into 1 molecule of nitrogen and 3 molecules of iodine. Now, back to something we looked at last week. How do I know that this breaks down into a nitrogen molecule and not 2 separate atoms of nitrogen?
Because it's not molecular elements?
Right. I had you label on your periodic tables last week the molecular elements. That is, the elements that come in groups when they're by themselves. Okay? Nitrogen is one of those molecular elements. Nitrogen comes as a 2. So does oxygen. So do all of the non-metals in group 17. Okay? All of these come as 2s. Phosphorus comes as a group of 4. And sulfur is a group of 8. Okay, so that's how we know. You do have to check back when you're doing a reaction to see, oh, is this one of the molecular elements? Do I need to put a little 2 beside it or a big 2 in front of it? Okay, everybody all right with that? Because if I wrote this reaction like this, it's still balanced, right? I still have the same number of both things on both sides, but it's wrong because that's not what it looks like. Okay? The real reaction produces a molecule of nitrogen, not 2 separate nitrogen atoms, and it produces 3 molecules of iodine, not 6 separated iodine atoms. Okay? Everyone follow the difference there? I often have people, like on a test, they forget which ones are molecular, they forget to check, and they write it the way I did in green there, and they get it wrong, and then they say, but Mr. Coderre, it's balanced. And I say, you're right, but the reaction is wrong. It's like me balancing something, but having it be completely wrong. Okay, it doesn't make sense. Even though, yeah, sure, I made sure everything was equal, it's not right. And just because the scale balances doesn't mean I did it right. All right, everybody follow me there? So knowing those, this is where we're going to start to use those molecular elements a bit more. All right, we'll do combustion reactions, then we'll take a little break. Okay, so this is those special elements there, guys, again, NO, okay, NOF, and then all the ones in group 17 that are nonmetals, okay, phosphorus and sulfur, and hydrogen as well. Remember, hydrogen is also one of the molecular elements and comes as a 2. All right, in a combustion reaction, you get fire. Okay, not always. A combustion reaction powers your cells, but luckily there are no fires inside your body. Okay, but we still consider it a combustion reaction if we are breaking down what we call a hydrocarbon in the presence of oxygen. Okay, we all know that in order for fire to live, okay, it needs oxygen. If you suffocate a candle, okay, or something like that, it will go out because the oxygen is not present to allow the reaction to continue. Okay. In any combustion reaction, you will always start out with a hydrocarbon. That is carbon and hydrogen bonded together in some kind of molecule. Okay, this particular molecule is propane. All right, it's the stuff you use in your barbecue. Right? And it is reacting with oxygen and the products of all combustion reactions. This is the beauty of combustion reactions. No matter how big this molecule is, the products are always these 2 things. Okay? All that will change are these numbers. Okay? If you have a really, really big hydrocarbon, like paraffin, candle wax is a really big hydrocarbon, these numbers would be much bigger. But it'll still be carbon dioxide and water. Anytime you burn something, the products are always carbon dioxide and water. Okay, now reading and interpreting this reaction. How many carbon atoms are in the reactants or on the reactants side of this reaction? 3. Okay, there's no number in front of that first molecule, is there? Okay, then we assume it's a 1. And there are 3 carbon atoms in propane. Right? How many hydrogen atoms are on that side? 8. Yeah, because there's no number in front of that, so it's a 1. There are 8 hydrogens here, okay? So imagine that this is a 1 in front of this. 1 times 3 is 3, 1 times 8 is 8. Okay, so there are 8 hydrogen atoms. How many oxygen atoms are there? 5 times 2 is 10. Okay, so there are 10 oxygen atoms. All right, so it's a little bit of math. Okay, it's not hard math, it's like times tables. Okay, but it's a little bit of math, 5 times 2. All right, on this side, on the product side now, okay, how many carbon atoms are there? Still 3. Right? There's a 3 in front of carbon dioxide. There's 1 carbon in a carbon dioxide molecule. 3 times 1 is 3. Okay? How many hydrogen atoms are there? 8. 4 times 2 is 8. Now the tricky one. How many oxygen atoms are there? Is oxygen in more than one place? Okay. That's why we have the plus sign. Okay? Balancing means I have the same number of things on this side and this side. It doesn't matter if they're together or not, as long as they're all equal on both sides of the arrow. So, how many oxygen atoms are there here? 6. How many are there here? 4. Is 6 plus 4 10? Is that how many we had on the other side? Then we're balanced, right? Okay, that's reading and interpreting reactions. We got to do a little itty bitty tiny bit of math. Okay, but it's not hard. Right? All we did was do a little bit of multiplying, and then we made sure that everything added up to the right number. Okay. So the trick with combustion reactions is that we balance them differently than the other 4 types. Okay? And we haven't even talked about balancing yet, but we're going to talk about the special rules for combustion reactions. In any other type of reaction, if I want to balance the reaction, I look at my biggest number and I start there. So let's actually look at that first. Let's say I've got this reaction here. Let's say right now, that reaction is not balanced. Okay, here's how I can tell. On this side, I have how many sodiums? 3. How many do I have over here? 1. So that's not balanced, right? I've destroyed 2 sodium atoms somewhere along the way, and I'm not allowed to do that. Okay, would the same be true for the calcium? Right, there's only 1 calcium over here, but there are how many here? 3. That's not good. That means I created from somewhere 2 calcium atoms, and I can't do that. So I need to balance this reaction. The way we do that is we start with the biggest number, which in this reaction is 3. Okay? Biggest number in this reaction is 3. So on this side, I have 3 calcium atoms, but on this side, I only have 1. If I put a 3 here, do I now have 3 calcium atoms on both sides? I do. But when I put that 3 there, did it also apply to the chlorine? Okay, so now how many chlorine do I have here? Okay. What do I need to put in front of the chlorine here, in front of sodium chloride to make 6? 6, yeah, because this is a 1, right? So I put a 6 there. Now I have 6 chlorines. 3 times 2 is 6. 3 times 1 is 3. Okay, that's good. When I put this 6 here, how many sodium does it give me? 6. Okay, so I got to come back over here. What do I need to put in front of this to get 6? A 2. When I do that, how many nitrogen do I have? 2. How many do I have over here? Now it's balanced. Now I got the same number, everything on both sides. Okay? And all I had to do was start with the biggest number and then just jump back and forth. Every time I put in a number, I have to change another thing until I'm finished. Okay? So all we did was jump back and forth and do a little bit of multiplying. That was it. Okay? That's how we do 4 out of the 5 reaction types. Easy. Combustion reactions work different. Okay? They have their own special set of rules because they just got to be different. Right? They're that kind of reaction. Got to be different. Okay, so in a combustion reaction, so I'm just gonna put a different one up here. Okay, I can't start with the biggest number in a combustion reaction, or it just won't work out. So, the first rule of balancing a combustion reaction, this you'll want to add to your notes. Okay, combustion balancing rules, there's only two, don't freak out. It's not like I'm going to put 8 rules up here, there's only 2 rules. Okay, the first rule, balance in alphabetical order. That rule will be the only rule you will need for half of the combustion reactions you do. All right, so if the first rule is to balance in alphabetical order, which element do I start with? C. Yeah, carbon is the first one in alphabetical order. So, how many carbon are there here? 5. How many here? 1. So what do I need to put in front of this to make 5? A 5. Okay, so I'm going to do that. Now my carbons are balanced. What comes next? H. Yeah, H comes next. How many hydrogens are there here? 12. Okay, how many over here?
2.
What times 2 is 12?
6.
All right. Now I can do the oxygens. It's all that's left. All right. How many oxygens are here? 10. And how many here? 6. What's 10 plus 6? Okay, so there's 16 oxygens over here. How many here? What needs to go in front of this to make 16? 8. Done. Okay, a little bit of multiplying, that's it. Okay, and one addition operation, you had to go 10 plus 6. Okay. Balancing in alphabetical order will work for 1/2. That will be the only rule you will need for 1/2 of all combustion reactions. Okay. Now, the other kind of combustion reaction you could run into would look like this. Pretty much the same. Right? I have a hydrocarbon, and I have oxygen, I have carbon, I have hydrogen. Okay? So if I start doing this and balancing in alphabetical order, let's just kind of see what happens. How many carbon here? Okay. How many hydrogen here? Okay. What do I need to put here? Okay. All right. Now if I look at my oxygens, how many oxygens here? Okay. How many here? 8. What's 8 plus 5? 13. What times 2 gives you 13? 6.5, right? Can you have half an oxygen atom? Or molecule even in this case? No, you can't. Okay? That's where the second rule comes in. Okay? This can't be balanced with whole numbers, and we always have to have whole numbers for balancing. So, we use what I call the rule of 2. Okay, because I'm a geek and I love Star Wars, and there's a rule of 2 in Star Wars. And what's the rule of 2 in Star Wars? It's about the Sith. Always 2 there are. Okay, a master and an apprentice. Well, for chemistry, the rule of 2 goes like this. If an even number of carbons you have, start with a 2 you must. Okay? Now you never forget it. I always do the Yoda voice and people do exactly what you did. Chuckle at me kindly. Okay, yeah. Okay, so. Okay? If you have an even number of carbon atoms, start your balancing with a 2. All right, I'll let you write that down and I'll show you what it means. Okay, so here's what this means. We start balancing with a 2. I'm supposed to balance in what order? Alphabetical. All right, so that means I'm going to put a 2 right at the front of this reaction, starting with carbon. Okay, now, how many carbon do I have? 8. Now, how many hydrogen do I have? 20. Okay, what do I need to put in front of this? A 10. All right, now, how many oxygen are there here? 16. Okay, and how many here? 10. What's 16 plus 10? 26. Okay, what times 2 gives me 26? 13. Now, I have a whole number. Okay, and now the reaction is balanced. And that is the lowest terms that that reaction can balance in because nothing will divide into 13. Okay? Everybody all right with that idea? Okay? It's just they've got these little separate balancing rules. Balance it alphabetically, and then the rule of 2. All the other reactions, find the biggest number, start there. Okay? And you just bounce back and forth. All right, I'm going to give you guys about, let's say, a 3-minute break here, okay? And then we're going to talk about the other 2 types of reactions before class. You can. All right, so the last 2 reaction types are very similar. Okay? They're both what we call replacement reactions. There's single replacement and there's double replacement, but they essentially work the same way. Okay? Replacement reactions always involve ionic compounds. Right? You will never have molecular compounds. You could have molecular elements, but not molecular compounds involved in a replacement reaction. Okay? The reason being, metals and nonmetals have to switch places in a replacement reaction. Something has to replace either the metal or the nonmetal, and you can't do that if you don't have an ionic compound. Okay, so in a single replacement reaction, the pattern will go as follows. There will be a single element, either metal or nonmetal, and it will react with an ionic compound. And your products will be a different element and a different ionic compound. Right? So the single element is going to replace part of the ionic compound, hence replacement reaction. Okay? So in this particular reaction here, I've got copper metal reacting with a solution of silver nitrate. Okay? This is a real reaction that happens.
Okay? If I put a strip of copper or a penny or copper wire or whatever in a solution of silver nitrate and leave it there and come back the next day, I will have a silver penny or a silver metal plate. Okay? The copper and the silver will switch places in the reaction. Okay? Usually what also happens is, because copper is going from being a metal to being part of an ionic compound, is the solution goes from being clear to what color?
Brown.
Not brown. What color are all copper-containing ionic compounds? Blue. Okay, so over the course of a 24-hour period, okay, the copper will disappear, silver will plate out onto it, and the solution will turn blue. As instead of having a solution of silver nitrate, after the reaction, you've got solid silver and copper 2 nitrate. Okay, so all that's happened in that reaction is the metals switched places. Okay, copper replaced silver in that reaction. Okay, everybody with me there? So in a replacement reaction, a single replacement reaction, the element that's by itself replaces the part of the ionic compound that it is like. So if the lone element is a metal, it'll switch out the metal. If the lone element was a nonmetal, it'll switch out the nonmetal. Okay? So in this case, this is an example of copper switching places with the metal part of that ionic compound. Okay, everybody all right with that? Okay, now here's the key part. In this type of replacement reaction, whatever this element is, metal or non-metal, it has to replace the part of the compound it's like. Otherwise, I won't get an ionic compound on this side. Okay, it has to go so that I make an element and an ionic compound. I can only have ionic compounds here. Okay, the copper didn't switch out the nitrate, and then I was left with silver and copper together. Metals don't bond to each other. I can't have that. Okay, the analogy we use, and don't take offense to this, chemistry is old-fashioned, okay, is the dance partner thing. Okay, so in this example, copper is this guy who's by himself, okay, and this is silver nitrate. Okay, this guy is silver, the girl is nitrate. Okay, after the reaction has occurred, okay, it's still boy, girl, okay, and again, chemistry is old-fashioned, there's nothing wrong with anything in real life being different than that, okay, but, okay, in chemistry, it's very old-fashioned, okay, it's very conservative, okay, so, in this case, I still have a metal and a non-metal together, okay, I don't have two metals together, okay, or two non-metals together. A replacement reaction doesn't work that way. Okay? It has to make an ionic compound, metal, non-metal, and then lone element. Okay? All right, so this is one where the metal, the element, sorry, was a metal, but I could also have a reaction that goes like this. So in this replacement reaction, the lone element was a nonmetal, right? And what happened was chlorine replaced the part of the ionic compound that it is like. It replaced the nonmetal, right? And what that ended up doing was putting nitrogen all alone and having calcium end up with chlorine on the other side. Okay? So whatever that lone element is, it just replaces the part of the ionic compound that it is like. Okay, everybody with me there? Is this reaction balanced? It's not. So, since it's not a combustion reaction, I start with the biggest number. Okay, what's the biggest number? 3. All right, so there are 3 calciums over here. How many over there? 1, so what needs to go here? Okay, when I put the 3 there, how many chlorine does it give me? Okay, so what needs to go in front of this to make 6 chlorine? Also a 3. Okay, how many nitrogen here? How many nitrogen there? Good, we're done. It's balanced. Okay, does it take much to do? Like the balancing, right? I start with the biggest number and I just go back and forth until everything is balanced. And then I just double check. All right, so that's the 2 ways a single replacement reaction can go. All you have to remember is the pattern. Element plus ionic compound gives different ionic compound in different element. All right, the last reaction type. Double replacement. Right? So very similar to single replacement, it's just now it's 2 ionic compounds that are going to react. Okay? These are actually a little easier to figure out because all that happens is the metals swap partners. Okay? In a double replacement reaction, you simply swap the metals and you'll have your new compounds on the other side. Okay? On this side, calcium was with chlorine. On this side, sodium was with chlorine. Okay? On this side, sodium was with carbonate. On this side, calcium is with carbonate. We just swap the metals, and we've got our new compounds. Okay? That way, we always make 2 new ionic compounds by just swapping the metals.
Is it only non-solubility, not this stuff? Not only solubility, but the stuff that are before, like naming?
Properties, solubility, naming.
So not,
Okay, is that making sense? So, like I said, we're gonna be working on reactions for a while. If today you feel like you're drinking from a fire hose, that's okay. Today is gonna feel that way, okay? But as we work on this a little bit more, okay, you'll feel less overwhelmed with it because you'll start to see that everything is very patterned, and as long as you know the patterns, you're gonna be fine with being able to write, balance, predict reactions, okay? Questions on the double replacement? Okay, is this reaction balanced? I think so. Okay, how many calcium here? 1. How many over here? 1. Okay, how many chlorine here? 2. How many chlorine here? 2, right? 2 times 1 is 2. How many sodium? 2. Okay, how many here? 2. And how many carbonates are there? There's 1, okay? Carbonate is CO3. That's why I asked this question, because that's a point that sometimes catches people, okay? This is carbonate, CO3. How many carbonates? That's why a lot of people like to put brackets around them all the time, because then they don't get that confused, okay? There are how many carbonates here? 1. How many carbonates over here? 1. Okay, so it's already balanced. Polyatomic ions sometimes throw a monkey wrench into reactions a little bit for people, and that's why I had that one on there. Okay. So we talked about balancing already. We're actually just going to kind of skip over this because we've been doing the balancing all the way along. Okay, it is something that we'll work on. Here's what I would like you to do. Write these reactions down as they appear here, and then tell me what type each one is. For right now, we'll just go with type. Okay, so write down those 3 reactions and tell me what reaction type they are. Okay, first reaction. What type is that? I've got 2 elements and they're reacting to form a single compound. You're right. Synthesis. Okay, synthesis reaction. All All right, what about the second one? I have an element reacting with an ionic compound. It's producing a different ionic compound with a different element. Single replacement, yep. All right, what about the third one? I've got a hydrocarbon reacting with oxygen, and it's producing water and carbon dioxide. Only one reaction type produces water and carbon dioxide. Combustion. Yeah, this is a combustion reaction. Okay. Let's have you write out these reactions in words. Here's what I mean. Okay, for the first reaction, this would be nitrogen plus hydrogen gives nitrogen trihydride. Okay, it's basically just naming. All right, we're just writing it out in words. So I'd like you to do the other two here before class ends. Write them out in words. You're just basically writing the names of the things that are in there. Now, one thing to notice here. Did I change the name of this just because there was a 2 here? No. Nitrogen's one of those special elements. It doesn't change its name. This is how nitrogen comes. Okay? It's always a 2 when it's by itself, so it's just nitrogen. Same with hydrogen. So for this one here, we've got nitrogen reacts with calcium chloride. So you just go nitrogen plus calcium chloride equals calcium nitride plus chlorine. Okay, we don't change the name. Okay, this is how chlorine appears when it's by itself. And then for our last one, we'll talk about it tomorrow. Good work today, guys.